Alright, let's take a look at a isosceles triangle here that's 90 degrees. And let's say we call one side 1, the other side 1, of course, because it's isosceles. Call those A and B. We're going to try to figure out what's C. Now, we all know this guy. His name's Pythagoras. He lived in ancient Greece about 2,500 years ago. And we've all used his theorem, a squared plus b squared equals c squared, to solve right triangles. So, if we try to solve this right triangle, we find that this hypotenuse ends up being the square root of 2. So that's all fine, but if we really think about the square root of 2, it starts to become a bit of a funny number. Well, a later ancient Greek, his name is Hippasus, started to look at this number more deeply, and he probably lived about maybe 100 years or so after Pythagoras. He was part of the school of philosophers known as Pythagoreans. And he wanted to know, like, what is the actual value of the square root of 2? So we all knew that the square root of 9 was 3, and the square root of 4 was 2, and so on. But the square root of 2 seemed a little bit more mysterious. So to do this, we should look at some perfect squares that we already know, get a sense of what a perfect square is. And here's from math.com, a little geometry take on it. So for example, 5 squared means 5 units by 5 units, which makes a total of 25 units. That's why we actually call them squares. If we go backwards, we call it a square root. So it's like an area worked down to a length. The square root of 25 is 5. As a quick example, we'll look at 10 squared. We know that means 10 by 10, which is 100. So if you square root 100, you end up with 10. And just a little note, another way of looking at this that you'll see later on in math is that a square root is actually just a power of a half. So really, when you square root something, you're raising it to a half power. Now, this brings us back to our little triangle and figuring out what the square root of 2 is. So what we do know is that the square root of 1 is 1, and the square root of 4 is 2. So if we think about it on a number line, the square root of 2 must be somewhere in the middle there and probably a little bit closer to the 1, to the left side. Some people call this a goalpost method. It's like you've got goalposts and you're kicking the ball in the middle. Now, we could take a guess and say, is it around 1.3? We can check by multiplying 1.3 by 1.3. Or realizing that 13 squared is 169, and it seems a little low. It's not quite 2. So let's try the next number. We'll try 1.4. Okay. So if we try square root of 2 is 1.4, and then we'll check 1.4 times 1.4, or we just realize that 14 squared is 196. We're much closer to 2 now at 1.96. We could try the next decimal up, which is 1.5. And that seems too big. That's 2.25. So we now know, okay, we're pretty close to 1.4 for the square root of 2. But is that the exact number? Now, we can, of course, check this on a calculator, and we find that it is close to 1.4, but there's a bunch of decimals after that. So what all those decimals are, is they're kind of funny. They're actually going on forever. They're never-ending decimals that are not repeating, which means there's no pattern to them. And this is what we call an irrational number. Now, it's said that Hippasus may have lost his life for proving this because the Pythagoreans didn't like the fact that numbers might not be as perfect and whole as they thought all numbers must be. Some people say it was put out on a boat, pushed off, drowned, maybe yelling root 2 to his death below, but whether this really happened or not, we'll never really know. It's one of those math myths that's floating around. Right, so, speaking of unlucky, let's try estimating the square root of 13. In this case, we know it's somewhere between 3 and 4 because square root of 9 is square root of 16. Sets our goalposts, and I'm going to guess it's a little bit past half. I can figure that out because 13 is a little bit closer to 16. I'll try 3.6, multiply it out. I'm going to get really close. It is, I believe, 12.96. So it was a good first guess. And know that there's more than one way to do this. There's a method you're going to see in your book that again, a later ancient Greek figured out that you can approximate pretty closely by using this formula, half a plus x over a, where x is 13 in this case, and a is basically the closest perfect square that you know. So in this case it's 4 because the square root of 16 is 4. If we plug these numbers in carefully, we'll end up with a half 4 plus 13 over 4, which ends up working out to a half 29 over 4, which is 29 over 8, which is about 3 5/8, or 3.625, I believe. Now we check it on a calculator as well, and it turns out that the square root of 13 is pretty close to 3.6. It's about 3.6, I think it is 05s. The reality is we don't really need all those extra decimals because they're going to go on forever and ever and ever. So just be careful when you're going to a certain amount of accuracy that you read. If you want 1 decimal, 2 decimals, and so on, and note that the square root of 13 is definitely irrational.